Good afternoon, everyone, from the Textile Institute at Manchester, UK, and welcome today to the second Tea with the TI webinar. Thank you for joining us. For those I've not had the pleasure to meet, I'm Stephanie Dick, the CEO of the Textile Institute. I'd like to thank our generous sponsors today, Taylor and Francis. We're delighted to have Nigel Bamforth with us today from Taylor and Francis, who's also kindly agreed to present midway through the programme to inform you all about the portfolio of the TI publications. So today the theme of the Tea with the TI webinar is technical textiles, as requested by our members and delegates following the last series of the webinars. The Institute's Technical Textiles Special Interest Group has put together today's programme. So we've joined forces for today's webinar to celebrate the relaunch of the Technical Textiles Special Interest Group. Charles Wood, the chairman of the group, will tell you a bit more about their work in the Special Interest Group. But before that, I'll just do a couple of housekeeping notes. Just to remind everyone who's joined us after Robin's brief intro, we're recording the session today, and a version of the webinar will be published on the TI YouTube page. The webinar is going to be about an hour to an hour and 30 minutes. As this is a webinar, your microphone and camera are in the switched off mode. So today you'll be hearing from 6 great speakers, and following the presentations, we'll then move to the question and answer session. For those familiar with Zoom, I think that's probably most of us now, please feel free to ask your questions in the Q&A feature on Zoom. As the presentations will take place, the questions will be collated and relayed to the presenters at the end of the webinar. For those that are not familiar with the Zoom setup, you'll find this usually at the bottom of your screen. And if we do not get a chance to have all your questions answered, we will forward these to the presenters, who'll be more than happy to respond and engage with you following the webinar. So I'd like to introduce Charles Wood, CTEX FDI, the chairman of our special interest group in technical textiles. Charles is a graduate of the University of Birmingham. He joined the family firm Boltex after 6 months technical warp knitting training at Kohlmeier in Germany. Boltex itself is well known for its work on 3D medical textiles, 3D spacer fabrics with specific compression properties and protective fabrics for FR and cut protection. During his tenure, Boltex has become a key producer of knitted technical textiles, winners of 3 Queen's Awards for International Trade. The company also won the Innovation Prize at the centenary celebrations of the Textile Institute in 2010 for its work on innovative 3D fabrics. Charles is also the founder, inventor, and director of Aerospring Medical Limited, which is based in Nottingham, who manufacture medical devices for the prevention of pressure ulcers. And I've been delighted to work with Charles for approximately 20 years now. So Charles, over to you.
Stephanie, thank you very much for that very kind introduction. And it's my great pleasure today to welcome you to Tea with the TI. So it's a newly formed committee. We're obviously rebooting the Special Interest Group for Technical Textiles. And I think it's a really good time to do this. There's a lot of changes going on in supply chains in the world, and we've got some wonderful speakers for you today. Just a point on Q&A, you may see some of the sessions being pre-recorded, and so we're actually going to take a Q&A session right at the end. So any questions that you have, please save those for the Q&A session, which will be at some point, probably around about after 2 o'clock. We're not exactly sure of the timings for that. So say welcome everyone who's able to join. And first of all, we're going to go into my presentation, which is about technical textiles in the 2020s.
So welcome once again to you all for joining Tea with the TI today. My name is Charles Wood, and I'm going to be presenting to you this afternoon the role of technical textiles in the 2020s. So the technical textiles market in the UK is the activity is estimated at £2 billion, and technical textiles forms part of advanced manufacturing in the UK. There are very close links and cooperations with areas like composites, advanced coatings, and material science, which are very prevalent in the UK, and particularly with innovations like graphene discovered in Manchester. There's a diverse base of companies ranged right across the UK, from Northern Ireland, Scotland, the north and west, northeast of England, and also into the Midlands and the southwest as well, who represent textile machinery, fabric formation, textile coatings, confection, and medical devices. In addition to this, the UK has some of the world's leading universities in technical textiles research, and this provides a very firm technological base. To provide a contrast, the UK, £2 billion worth of economic activity out of the total for textiles of £9 billion, compares with £22 billion in Germany. And the quote here from the CEO of Messe Frankfurt highlights the importance that the Germans place on technical textiles, and this has been a nationwide drive over the last 20 years. The 2020s are going to be a time of very significant change. As we pull out of the pandemic, technical textile technologies will provide some of the key solutions to some of society's challenges. And this is particularly true of climate change. Just recently at COP26, I was really inspired by David Attenborough's speech and his quote that we are, after all, the greatest problem solvers to ever existed on Earth. And I think this highlights the opportunity that there is, and technical textiles can play a part in actually halting carbon emissions, which is the target for this decade. So some of the areas which I've picked out, opportunities for 2020s. First of all, construction. It might surprise you a little bit, using composite reinforcements. Secondly, energy generation. There's obviously wind turbines, but there's also green hydrogen, and there are other technologies which we'll come on to. Then electric vehicles. Electric vehicles might seem quite obvious, but there's a lot happening in this area, and also with battery technology as well. And then finally, in the health area, remote health monitoring using smart textiles, which provides greater feed of information for medical staff and improved patient care as well. So to the first area, construction. Construction actually produces around about 10% of the global emissions of CO2. Textile reinforcements are already being used and can provide an important contribution to lowering carbon emissions in construction. Cited example is Knitcrete from Zurich, which uses a knitted aramid fabric to produce a concrete mold, saving about 250 hours of processing time, and eventually a textile reinforced bridge, as seen in this image. There are many projects which are being run on the textile reinforcement of concrete and in construction, and one notable one is textile beton, which has been run in Germany, using a variety of different materials to provide new solutions in the construction industry. In this market, the market was estimated in 2020 at $17 billion, and that's projected to grow by 2026 up to about $24 billion. So an annual growth rate of 6%. It may actually turn out to be quite significantly more than that. The next area I want to focus on is energy generation. Technical textiles are already embedded in the renewable energy sector. Glass and carbon fiber fabrics are extensively used in the wind turbine blades and in the nacelles. Energy actually represents 20% of all emissions, and we know that the move to renewables is going to accelerate over the next few years. Interestingly enough, the US government has recently estimated that the fastest growing job category in the country is a solar power technician, which is closely followed by a wind power technician. We're also recent developments using natural fiber wind turbine blades or nacelles, and there's one which has been produced in Germany by a company called Green Boats. And we're going to see a lot more of this with natural fiber composites coming more to the fore. Aside from wind power, the new energy industry is going to be very broad and diverse. One particular area of interest is green hydrogen, which I know the government in the UK is focusing on a lot. And technical textiles is going to play a key part in all of these new areas, whether it's pultrusion to manufacture cylinders, whether it's membrane technologies used in the production of green hydrogen. Some of these things are still to be developed and still to be commercialized. Turning to electric vehicles, we know that the 2020s is going to be a time of considerable disruption, and many new companies and services will come into play, whether from car sharing apps to new players coming into this field. So it's not just going to be the Teslas, Jaguar Land Rovers, the Volkswagens, the Hyundais of this world who are already taking significant market shares in electric vehicles, but also there'll be many new companies as well. One notable example is Arrival, a company based in London, which is a new company, about 700 employees. And at the heart of their technology is actually polypropylene and glass fabric, which is used for exterior panels, recyclable, and it's creating new pathways into this market. Then finally, in the area of health, remote health monitoring using smart fabrics and textiles is something which we're going to see a lot more of. The market in remote patient monitoring is expected to grow to $7.3 billion by 2028 from a base of $2 billion in 2020. That's an annual growth rate of approximately 16%. And investors like Berkshire Hathaway are looking at this area. There's going to be a new breed of super smart textiles which will be able to monitor body movements and remotely transmit the sensor signals while powering their own operations by absorbing energy from the natural motion of the wearer. We all know the pressures that the health industry is under, the health sector is under, and I think this new technology, when it's ready, will be greeted very favorably. All the categories for technical textiles have really been formed by Messe Frankfurt, who started the Textile shows back in the 1980s, late 1980s. And they first categorized technical textiles into these 12 different areas. I think it's probably time to revisit these categories, to redefine them. What does technical textiles mean for us today? We have a category like Ecotech, just one category. It simply no longer fits purpose. So I'd like to ask, if anyone's got ideas or how we can approach this topic, because I think that to identify where the opportunities lie is one of the first parts. And this is something I hope that we will do with our work with the Technical Textiles SIG. So thank you all for listening. And I think we're going to have questions at the end. Thank you very much.
Okay, so that concludes the first session, and as I say, we'll be taking questions later on, as we've already stated a couple of times. So next, it's my very great pleasure to introduce Professor Stephen Russell. Stephen is Professor of Textile Materials and Technology at the University of Leeds, and his areas of expertise are textiles and non-woven fabric engineering, particularly textile product design for healthcare, consumer industrial sectors, as well as sustainability and fashion and textiles, with many papers published and leading a research group which consists of 25 PhD students. So we'll pass over to Stephen for the next talk, Adversity and Opportunity.
Hello, everyone. I'd like to give you a brief update on recent developments in the non-wovens industry, which of course is an important and growing part of the wider technical textiles industry. My focus today will mainly be on developments in Europe, but given the globalized nature of the industry, the key points are still applicable, including of course in the UK. Well, I think it's fair to say the last 2 years or just less have been unusual, to say the least. And since the pandemic hit, there really have been winners and losers in the industry, at least in the short term, with some markets accelerating and growing very rapidly while others have been badly disrupted. Today, what I'd like to do is have a brief look at some of those markets. And I'm going to focus mainly on Europe, but the global nature of the industry means that the main messages are pretty similar. I also want to look forward and mention a few areas that are both challenges and opportunities, and point to one or two technological developments as we go. The non-wovens industry has grown year on year in the last 20 years, with the exception, I think it was of 2009, due effectively to the credit crunch. But essentially, there's been 15 years of continued growth. Partly a result of the pandemic, 2020 saw non-woven fabric output in Europe increase by over 7%, which is a very large figure. The last 2 years have also been significant in that there's been a large amount of investment in new manufacturing capacity, including orders for new lines in the UK. But there have also been major supply chain disruptions in some markets, many of which are far from over. Markets for non-woven fabrics really do span a multitude of different products with varying operational service life requirements. What I'm showing here are just broad market headings. The ubiquitous presence of non-wovens inside industrial, healthcare and consumer products is really easy to overlook because they're quite often buried outside as part of a composite structure. But single-use short life absorbent hygiene products, or AHPs, and disposable wipes still consume a large proportion of overall non-woven production. And the markets that I've highlighted here in bold grew particularly sharply from 2020, due in large part to the effects of the pandemic, driving up overall non-woven output, even though other markets were negatively disrupted. Well, where would we be without melt-blown non-wovens over the last nearly 2 years? The demand for EN 149 compliant face masks and other PPE, not surprisingly, meant that the output of non-woven fabrics for medical applications boomed in 2020 onwards, building on what was already a growing market, including wound dressings and various other medical devices. The pandemic has created enormous ongoing demand, with electrostatically charged melt-blown filter media required for FFP3 and equivalent masks. Manufacturing these composite spun-bond melt-blown filter media shown in the slide also requires specific grades of polypropylene resin, usually with high melt flow rates, and production equipment with the ability to electrostatically charge the fibres. So it's not as easy as it first seems. And in addition to medical non-woven output, there's grown in other markets, probably due to increased concerns about air quality, hand hygiene and surface cleaning, but also potentially in the case of HPs due to bulk buying by consumers who feared shortages during the pandemic. Not surprisingly, output associated with the production platforms making fabrics for the growth markets has also increased. And we're talking about high production processes here. I mean, for new spun bond systems, maximum take-up speeds are reaching 1,400 meters per minute. That's at the winds are equivalent to about 270 kilograms per hour per meter working width of the machine. But as we all know, there have been massive supply chain disruptions leading to reductions in output in some markets. This shows what happened to European car production in 2020 with further issues in 2021, and the knock-on effects for the non-wovens industry, especially in just-in-time supply chains, are predictable. In 2020, there was a major drop in European output of non-wovens for automotive interiors, and of course, besides headliners and interior trim, non-wovens serve many other purposes within the vehicle. Other supply chains and markets were also disrupted, but for different reasons. One of the difficulties for garment interlinings has been, if you like, the casualisation trend, since less formal garments contain no or not as much interlining material. And this trend has accelerated over the last 2 years. Looking forward, here are a few areas driving R&D and innovation. Not surprisingly, clean air remains a major topic, not just relating to masks, but also to air purification systems and heating, ventilation and air conditioning too, HVAC, for public spaces. New products are needed to deliver UN Sustainability Development Goals, not least because the SDGs are also influencing corporate strategy, investment decisions and public policy making. Obviously, managing natural resources and emissions not only brings environmental benefits, but also potential for cost reduction in production. Greater agility in non-woven manufacturing should also become more feasible as digitally connected smart factories continue to develop. Finally, environmental legislation is being increasingly influential in determining what polymers we select and how end-of-life materials are managed and recycled. In relation to European regulation, the EU launched the Single-Use Plastics Directive, which affects products such as sanitary towels, pads, tampons, applicators and wet wipes for personal care and domestic use, and involves extended producer responsibility. It also adopts a very strict definition of plastics, only excluding non-wovens containing natural polymers that have not been chemically modified, which favours increased use of wood pulp and regenerated cellulose fibres rather than bio-based synthetic fibres. Elsewhere, though, I think we can expect to see a gradual rise in non-wovens containing bioplastics, particularly with polymers compatible with existing melt spinning and spun melt manufacturing platforms which predominate in the industry. This includes bio-based aliphatic polyesters made with bacterial fermentation of renewable materials such as PHA. Digitally controlled processes are also emerging that allow the regional composition and structure of a non-woven fabric to be more precisely customised than is currently possible in conventional web forming and bonding systems. These are just two examples of dry continuous processes working with preformed webs or fabric. In the Fiberline system, an alternating electric field migrates and mobilises small particles such as superabsorbent polymer in the fabric to modify bulk physical properties. In the DLO 3D lofter, short fibres are pneumatically deposited in discrete locations onto a moving pre-needled fabric to enable 3D effects and patterning prior to final bonding. In some ways, these might be considered to be examples of continuous additive manufacturing at scale. So to summarise, overall, despite significant disruption, non-woven output has grown substantially through the pandemic, driven largely, but not only, by increased demand in medical and hygiene markets. We've also seen significant investment in new production lines in the last 2 years, including here in the UK, effectively shortening supply chains. And dialogue about the role of digital smart factories in the non-wovens industry has accelerated too, as well as within this looking at prospects for better opportunities for customising and differentiating non-woven materials. And finally, given the industry's high dependency on plastics, environmental legislation and policy making will continue to have a major influence on how we design and manufacture non-woven products and how we deal with their environmental impacts during manufacture, but also at the end of life. Thank you very much for listening. I hope this was helpful.
So many thanks, Steve, for that excellent presentation on a particularly dynamic sector, non-wovens, which is clearly leading the way in terms of the digitalization of manufacturing, but also in terms of the agility as well. So on next to our next presentation is our sponsor, our event sponsor for today. We're extremely grateful to Taylor & Francis, and we have Nigel Bamforth, who's with us. Nigel joined Taylor & Francis in 2021 as portfolio manager, working on a range of journals covering physics, material science, and chemistry. Nigel has wide experience in the publication and development of scientific books and journals, portfolios for companies including Chapman & Hall, Wolf Publishing, Blackwell, and Wiley. So over to you, Nigel.
Hi, everyone. Good morning, good afternoon, good evening, dependent upon where you are in the world. As Charles said, my name is Nigel Bamforth. I'm a portfolio manager for Taylor & Francis, and I'd like to thank the Textile Institute for this opportunity to just talk a little bit about the publications that we publish for the Textile Institute. Next slide, please. So just a little bit about Taylor & Francis. So we partner with world-class authors basically researchers, scholars, professionals operating at the top of their fields. And we publish in all areas of academia, really, science, technology, humanities, social sciences, and so on. We're also one of the world's leading publishers of scholarly journals, books, ebooks, textbooks, and reference works. Next slide, please. So the Textile Institute's publications, we publish basically 2 journals and a book series for the Textile Institute. The journal of the Textile Institute, Textile Progress, which is a journal, and the book series, which is called Professional Publications of the Textile Institute. Next slide, please. So starting with the journal of the Textile Institute, we publish innovative research, also professional interest papers for the textile community, and the journal covers areas such as science, engineering, economics, management, and design relating to textiles. Next slide, please. So the journal publishes 12 issues a year, roughly 180 papers published per year, and we have an impact factor of 1.88. Next slide, please. Textile Progress. Textile Progress, we publish comprehensive reviews in all aspects of textiles and the associated science and technologies. Next slide, please. So this journal publishes 4 issues per year. Each issue contains one very comprehensive review paper. Next slide, please. So the book series, the Textile Institute's professional publications, the editor-in-chief is Helen Rowe, who is the vice president of the Textile Institute. Next slide, please. And basically, these books provide support to textile professionals in their work. They help emerging professionals, and they provide information needed to gain a sound understanding of key and emerging topics. Each book is written by an experienced author or authors who have expertise in the subject area. And before publication, each book is independently reviewed by textile professionals or academics. Next slide, please. So this is a list of some of the recent and forthcoming titles. You'll see there's some really important subjects there. The bottom one particularly vitally important, the use of textiles in personal protective equipment, face masks and so on, which is absolutely key, vital, and important for the current fight against the global pandemic. Next slide, please. So just a little bit about what we actually do as publishers, apart from publish the great work of the Textile Institute. Next slide, please. So our marketing objectives at Taylor & Francis are to demonstrate impact, to grow international reach, to attract high quality submissions to the journals and book series, to drive citations to the published work, and also to facilitate author and researcher engagement, and also for the Institute to actually increase membership and promote the Institute through our activities. Next slide, please. This is a really interesting one. I think that, and I always got very proud and amazed when I share this, that Taylor & Francis website is now in the top 500 most visited websites globally, which is quite extraordinary. As you can see from that graph there, we're ahead of some of our competitors. We're doing very well and increasing all the time. Next slide, please. Another interesting slide, I think, is this one, is that visits to our website, 25% of the visits now come from mobile devices. So we've developed something called an e-reader, which provides proper access at scale, if you like, on a smaller mobile device. Next slide, please. Reaching readers, so you can sign up on our website to receive subject-specific emails containing information about the latest articles published by us in your areas of interest. So you can select subject areas and so on, and receive a newsletter every couple of weeks. Next slide, please. We also send citation alerts to paper authors when their articles are less than 2 years old, when their work has been cited in another Taylor & Francis journal. Next slide, please. We've got social media accounts on all these platforms. The two bottom ones there, WeChat and Weibo.com, we post in the Chinese language in those two Chinese-based sites. Next slide, please. We're also very proud to be involved in some development initiatives, which basically means that we're providing publications at a reduced rate or free for all to view in some of the world's developing nations. So the top right one there, Research for Life, is probably the most famous one, I guess. And you can look at all these online just by Googling those terms. Next slide, please. So we have a huge wealth of information on our website, www.tandfonline.com. That's the main website address. There's information there for authors. So if you're interested in submitting a paper to one of our journals, for example, if you're a journal, work on a journal, there's resources for editors, resources for librarians, and so on. It's all free. It's a huge amount of stuff. If you're interested in submitting a book proposal, for example, there's a form you can find on the Textile Institute's website. And there's full instructions on how to submit papers to the journals that we publish for the Institute on the Taylor & Francis website. Next slide, please. So I'd just like to finish my brief presentation just by thanking the Textile Institute again, and just to say how proud we are as a publisher to be associated with the Textile Institute and to be able to sponsor events like this. So thank you very much indeed, everybody.
Many thanks, Nigel, for your presentation, and equally we appreciate the support for the TI as well today. I know for one, I need to catch up on my reading there. So on to our next speaker, Jason Kent, who is the CEO of the British Textile Machinery Association. And Jason's going to be speaking to us today about the evolution of artificial grass. With over 35 years experience in the carpet tufting machinery industry, Jason Kent has worked in various roles for Cobble and Van der Velde Group. From product design to managing director, Jason's been a prominent figure in the carpet manufacturing industry, helping clients adopt a mass customization approach to their production. As CEO of the BTMA, his current role involves delivering the strategic goals of the association, enhancing membership value, and broadening the network opportunities for the textile machinery sector. We're very grateful to Jason for allowing us to host some of the early meetings at the BTMA. There's a wonderful range of members for that organization. Over to you, Jason.
Hi everyone, I'm Jason Kent and I'm the CEO of the British Textile Machinery Association. Having worked in the carpet manufacturing machine industry for 35 years, I'd like to give you a very brief overview of a well-established technical textile, and that is artificial turf or artificial grass, whatever you want to call it by. Artificial grass has been around for a long, long time, so that gives me the opportunity to explain about the evolution of the product as we now start to see the introduction of the fourth generation of systems in sports stadiums and other venues around the world. Searching for the goal of realism and resilience, like most evolved products, there's not only been developments and innovations in the process machinery itself, but also in the raw materials. With sustainability dominating our lives, we will see that the evolution of the product has come full circle in a roundabout way with hybrid systems, but more about that later. The popularity of artificial turf came about primarily because of its maintenance-free properties and consistent characteristics throughout the seasons, no matter the geography of the climate. Time is money, as they always say. And although investment costs have been high, particularly in the regulated sports sectors, the return on reduced maintenance costs and high pitch availability, as we call it, throughout the seasons makes for a very, very strong justification. Applications are countless for the product, particularly now domestically supplied product has become cheaper and is much more widely available. You'll have seen a lot of this product in garden centres and hardware superstores now, surely. but no pun intended here, but for sure its uses are growing, everyone. The worldwide market distribution, though, is quite difficult to capture in terms of growth, particularly since there is significant ongoing replacement of existing sports installations, and that brings with it the headache of how the old product is going to be disposed of. What I want to get across, though, with this simple pie chart is the fact that sports playing surfaces continue to dominate the market in terms of square metres of product, although landscaping is the smallest sector, it is actually the largest sector of growth. We're seeing a lot of nations now with arid landscapes transform their unfertile areas into flourishing looking grass vistas. You know, it's great for business investment propositions and certainly for tourism. Now, artificial grass, as I said, is one of the oldest forms of modern day technical textiles, and it dates right back to the 1960s, where famously the first application of such a product was for the baseball field in the Houston Astrodome. You'll have heard of AstroTurf for sure. Its technical name at the time was called chemgrass. Now, artificial grass, or plastic pitches as they were nicknamed, gained popularity in the 70s and 80s, but that popularity quickly turned to criticism and negative press. Here in the UK, the first professional league football club to have a plastic pitch installed was actually Queen's Park Rangers at their Loftus Road ground. That was back in 1981. It was trademarked at the time as OmniTurf, and this pitch, along with several others around the country, they quickly garnered accusations of extreme home bias relating to excessive ball bounce and certainly friction burn related injuries to players. Plastic was definitely not fantastic, lads. Sorry, Terry Venables. And by the early 1990s, every UK professional league football ground had removed their artificial playing surfaces back in favour of real grass. In the 1990s, the artificial grass industry, though, was by no means dead, and a solution to these problems was quickly developed. Although the solution added complexity to the installed product structure, the third generation systems that are widely popular today were highly consistent in their playability characteristics. The manufacture, supply and installations of association playing surfaces, though, are highly regulated through license by FIFA and by the International Hockey Federation, amongst others. And just to demonstrate how scientifically regulated these playing surfaces are, here are some examples of the testing equipment that's used. You can see the Lisport tester, for example, on the third photo, and that simulates football boots that have been pushed and slid sideways into the playing surface. What's also taken seriously too is the impact of injuries on the human body and whether the physical characteristics of the playing surface actually change over time and under extreme weather conditions. Now, moving on to other and more recent applications of artificial grass, perhaps you already have, or know someone, or have seen installations of domestic lawns and roof terraces. It's lifestyle driven for sure, and it gives a new dimension to those who want a green, luscious and maintenance-free lawn all year round, or for those people who are not able to have a real lawn without incurring exorbitant costs. Certainly artificial grass has gained popularity with public and corporate events too. A picnic in the park concert can now become a picnic in the car park, for example. And there was an abundance of the product used at the recent COP26 conference in Glasgow. But not very eco-friendly, you quite correctly think. Well, the statistics are shamefully there for you to see, everyone. The problem's not going away, and it's been ignored for too long. And traditional methods of disposal have certainly fallen out of favour. So far as the recycling of previous generations of products are concerned, the act of greater awareness within the complete supply chain of the industry has actually yielded some innovative solutions, although it is only at the tip of the iceberg at the moment. Initiatives like the ones shown here have become expansions of existing businesses with artificial grass installers. They are now providing a complete turnaround service for both their clients and product manufacturers. Synthetic yarn manufacturers have now started to develop materials that are biodegradable after a specified period of time, whilst other manufacturers, they're focusing on materials that are truly circular and they can be stripped, cleaned, reformed back into granules and then re-extruded back into grass yarn. And yes, I did say yarn, because artificial grass really is classed as carpet. It is produced by traditional carpet manufacturing processes. The difference is that the pile height of the carpet and the pitch between the tufts is much larger. That's the only difference. Other than, of course, the yarn texture is different to that of domestic and commercial carpet, but traditionally still manufactured from polypropylene, polyethylene, or polyamide yarn, which is also found in everyday synthetic fibre carpet. Like traditional carpets, though, we get the same variability of quality and cost, hence the need to stringently regulate the product for top-level sports. Generally, it always comes down to raw materials so far as cost and quality is concerned, and the manufacturing process is pretty much established if the machines are well maintained and set correctly. And out there are some truly terrible examples of landscaping and leisure products, as well as examples that can be found in schools and parks. Just like carpet, there are two production methods of producing artificial grass. Tufting is the predominant method, while weaving is starting to make its presence in this sector. The tufting production method is favoured for its very high production output, flexibility of product quality changes, and is a relatively low investment in costs of capital equipment. A tufting machine is capable of producing up to 2,000 square metres of product every hour. The downside to the tufting method is that traditional processes are needed to secondary back the product in order to lock the tufts in position so they don't fall out. This extra process does come at an additional cost of capital investment and materials, and it's not cheap. The weaving method of production has relatively low output in terms of square meterage compared to that of tufting. Also, the capital investment for machinery is much higher to that of tufting. However, the weaving method benefits greatly from locking the tufts into the weave shed as the product is produced, so it doesn't need additional finishing processes. And also, the method of colour of yarn selection by an electronic jacquard allows touch lines of any shape and size to be woven into the product, as you can see on this photograph below. We're now starting to see the fourth generation of artificial grass product being introduced in installations around the world. The highly successful third generation of product was complex in its installed composition, as you can see in the top photographs, with a number of levels of different substrates. With the fourth generation product, however, a mix of fibres using traditional grass yarn and frise yarn gives a more realistic appearance while creating the ideal cushioning and ball handling characteristics, but without the infill. Frise yarn, though, is difficult to manage in the production process, but its disadvantages are outweighed by the advantages of a much reduced installation in materials and certainly post-installation costs. Now, the next natural step is indeed going to be more natural than ever before, and that's a hybrid grass yarn system. A hybrid system of natural grass is contained in a matrix of synthetic grass, and it has special backing properties to allow the natural grass roots to grow through from the soil below. This prototype, fifth generation, if you want to call it, product, it's creating a lot of excitement and interest in the market, as the advantages are quite many. Being as close to a grass plane surface as you can get, these synthetic fibres help make the plane surface a lot more durable throughout the sports season. Early trials also suggest that the plane surface doesn't need to be replaced by up to 3 times the plane hours to that of a traditional 3G plane surface. And when it does need replacing, there's significantly less synthetic fibres to recycle. I think it's actually a fantastic example of where technical textiles can be successfully integrated into a widely used organic product. So what do we think the future is going to look like? Well, for sure, it's certainly going to be full of smart textiles. With the development of smart yarns and intelligent packing materials, it's not inconceivable that artificial and hybrid playing surfaces of the future will have inbuilt monitoring capabilities, and the installation itself will inform us when and where any maintenance is required. Another thought is, and it's already been developed within the hospitality and corporate carpet sectors, light transmissive and polymorphic yarn fibres could give the possibility to turn an artificial grass playing field into a multitude of different layouts for different sports and events. A football pitch 1 minute, 2 hockey pitches side by side the next minute. Again, no pun intended, but this could be an absolute game changer. Okay, enough. So I hope this presentation has been interesting and has been an insightful look into what I think is a very versatile technical textiles. It's often overlooked, taken for granted, but it's becoming a larger part of our lives. I'm sure you'll come across many other applications of artificial turf, some more practical than others, certainly if you look at some of the photographs there. Thank you very much for your time, everyone.
Well, I'm quite sure by now you must be absolutely itching to ask some questions. So please, for those of you who are frantically scribbling notes, you can put a question on the Q&A function, or also you can put a question on the chat function as well. So thank you very much to Jason for that excellent presentation. Smart grass, I'll certainly be changing my view when I'm watching the football next time. So now over to the other side of the Atlantic, and I'm very pleased to welcome today Robert Hines. Robert Hines, CTEX ATI, serves as Director of Research and Development and Textile Supply Chain at National Safety Apparel, a provider of comfortable flame-retardant garments. Robert has a master's degree in textile technology from the Institute of Textile Technology and a Bachelor of Science degree from the University of North Carolina at Chapel Hill. He has over 30 years of domestic and international experience in textile product development, quality, and manufacturing, and is credited with numerous US and world patents and publications. Most recently, Robert's work is focused on the development of fabrics and garments that are both protective and comfortable while providing protection from arc flash and flash fire hazards. We're very pleased to welcome Rob. Thank you very much, and over to you.
Hi, I'm Rob Hines, and since 2008, I've been developing flame-resistant textile fabrics and apparel. During this time, protective textiles have evolved from bulky, uncomfortable, and some might even say unsightly clothing to apparel on par with leading brands. So it's great to have the opportunity today to talk about how comfort and style have and continue to spur innovation in protective clothing. So to start, I want to spend a minute and talk about the things I'll be covering. First, to understand this area of technical textiles, it's important to know the hazards faced by the end user. So in this case, it's flame and thermal. Next is the problem of compliance, or getting people to wear their PPE. Finally, I'll cover innovations that have helped solve this problem of compliance. So as I said, understanding FR clothing starts with the hazard, which is a flame. So naturally, the fabric must be flame resistant. But what exactly does flame resistant mean? Well, really there are two important things about flame resistance. Number one, it needs to self-extinguish. Number two is it should not melt or drip after exposure to the flame. Now, this is going to exclude a high percentage of thermoplastic fibers like polyester and nylon, because when they burn, they melt and drip. And what happens with melting and dripping is it will make an injury worse because that molten material gets onto the skin and causes a more severe burn. So instead, FR fabrics use inherently flame-resistant fibers like aramids or monocrylics, or sometimes cotton fabrics are used, but they're treated to be flame-resistant. In both cases, the same key features. They self-extinguish and they don't melt or drip. Now, in addition to being flame resistant, it's also important for FR clothing to provide a degree of thermal insulation from the hazard. So this typically means a rating as to the level of protection offered by the garment. The first hazard I want to talk about is an arc flash. Now, an arc flash is caused by an electrical fault. And what happens is ionized conductive plasma is generated, and it's a temperature in excess of 5,000 degrees Celsius. It usually lasts less than a second, and it can ignite non-FR clothing, causing severe burns. Now, you might ask yourself, 1 second, how bad could that really be? So to demonstrate, I have a short video of an arc flash. Now, in this video, you're going to see two different pieces of clothing. On the left hand in the orange is a non-FR coat, and on the right in the yellow is a flame resistant coat. Now, what you'll see is after the arc flash, that orange non-FR coat is going to ignite. It does not self-extinguish. And you can also see this evidence of melting is dripping. Little bits of material will drip down, and you can really see that well. So let me cue up that video. So again, the orange is the non-FR. There's the arc flash. And you can see that orange non-FR coat caught on fire. It's not extinguishing. And you can see little bits of molten material kind of falling away, dripping down. Whereas on this other side, FR coat is self-extinguished. Now, the next hazard I want to talk about is a flash fire. These happen when combustible gas is released and finds an ignition source. Good example might be someone drilling for oil. They hit a natural gas pocket, and if they're unlucky, they get a spark. Now, flash fires typically last 3 seconds or less, and their temperatures range between 500 to 1,000 degrees Celsius. I also have a good video so that you can get a feel for what flash fire is like. Here, this is some FR coveralls. You can see the flash fire hitting it. And of course, with the FR coveralls, they're going out. But that gives you kind of an idea of what a flash fire looks like. Very short, but very intense hazard, just like an arc flash. So who needs FR protection? Well, the hazard we just discussed show up in electrical, oil and gas, mining, and the military sectors. Arc flash is a concern for end users who work with electricity. So the clothing is rated according to how much arc flash energy it can see and still provide that sufficient level of protection or insulation from the heat energy. On the other hand, users in oil and gas, mining, and the military, they're more likely to be concerned about flash fires. Here, the clothing is tested in the lab, like the video you just saw. And what you didn't see is there are sensors underneath that coverall distributed all over that mannequin. So the sensors are reading how much heat energy is coming through that coverall, and a calculation is made as to how much burn a person would receive. And this is another way to quantify the level of thermal insulation provided by that flash fire coverall. So now we've looked at two pretty awful hazards faced by end users in this heat and thermal space. So why, when faced with all of that, why in the world would you not want to wear your PPE, your personal protective equipment? Well, in an effort to provide adequate protection, flame-resistant clothing has tended to be bulky, heavy, hot, and uncomfortable. Now, combine that bulky, heavy clothing with the fact that you're exerting a lot of effort to do your job, and frequently this is in a hot environment, and you get the problem: compliance. A 2016 survey found that 90% of safety professionals and users observed workers not wearing the appropriate personal protective equipment. The number one reason for non-compliance: lack of comfort. That was followed closely by it's too hot doesn't fit well, and it's just plain unattractive. So solving those problems has been the main driver behind innovations in PPE. Now, what are the risks of not being compliant? Well, obviously, there's this significant risk of personal injury. And along with that comes a cost. Even a single minor incident can average over $100,000. That, in addition to the damage to morale, to the reputation of the company. But if the injury is more severe, costs can range into the millions of dollars. So innovations that help drive compliance are really important. So what are those? Well, performance, lighter weight fabrics, denim fabrics, and garment styling. Better denim, better garment styling. So let's jump into performance. Performance FR has taken the moisture wicking and fast drying technology developed by the sports and outdoor industry and applied it to flame resistant apparel. As I mentioned, like athletes, PPE users are exerting a lot of physical effort, frequently in very hot environments. So moisture wicking, quick drying fabrics help them stay cooler. And because this moisture evaporates, it takes heat with it as it dries. And that's this idea of evaporative cooling. So it's helping that end user, again, stay cool while they're working hard in this hot environment. Staying dry is also way more comfortable. If you've ever worked out in a cotton t-shirt, which retains that sweat like a sponge, you know exactly what I'm talking about. Hate to be wet. So over the years, different technologies have been applied, including inherent moisture wicking technology at the fiber level, as well as chemical treatments, although the latter have a tendency to wash out before the garment wears out. Another innovation are lightweight fabrics with the same level of protection. Now, logically, you would think that lighter fabrics should be less protective. After all, we're talking about insulation here. And, you know, that's normally the case. But new discoveries have made a significant impact. Over the last 5 or 6 years, weight has dropped between 35 and 45%, while maintaining the same level or equivalent protection. And many new fabrics have entered the marketplace, and these have been really a boon for end users because lighter weight garments are a lot more comfortable. They're cooler, they're less physical load to carry, and they can improve mobility. Another plus for compliance. As one of the first workwear fabrics, denim has always been important, but historically FR denims have tended to be basic, vanilla, and should I say dad. Fashion elements were limited by the FR technology, but thanks to new innovations, including hybrid fabrics, incorporating inherent fibers, new FR denims look and feel as good as your favorite pair of casual jeans. Options now include different garment washes and distressed sanding finishes. In fact, the FR denims were one of the first fabrics to incorporate stretch, which is another huge factor in comfort as well as mobility. Style is the final and most basic of the innovations. Gone are the days of generic one-color coveralls, and PPE now reflects contemporary styles and colors. Instead of going home and changing, you can go straight from your job to the pub without missing a beat. Yet another tool to increase compliance by getting users to like wearing their PPE. So that concludes my presentation on how comfort and style drive innovation in protective clothing. And in closing, I'd like to thank the Textile Institute for the opportunity to present, as well as to participate in the Technical Textiles Subject Interest Crew. I'm really looking forward to getting to know my colleagues better as we explore new materials, technologies, fabrics, and finishes, and maybe we find some new innovations we can apply for protective clothing. Now, I would love to hear any questions you might have. Thanks a bunch.
So very many thanks to Rob, who's one of our committee members. We're very pleased to have him on board, and also to build those international links with the United States and of course with many other countries as well. And we see we've got people from other parts of the world, and the Technical Textile SIG will be looking to foster and encourage and grow those links internationally as an important part of what we do. On to our final speaker today. It's Simon Burnett Boothroyd, who is a course instructor for the TI, for the Textile Short Course, Excellent Textile Short Courses. Simon is a consultant with a broad spectrum of textiles. He has expansive portfolio in the development of products from medical specialisms to high-performance outerwear fabrics. Simon is a patent holder in woven fabrics in the PPE market and currently sits on the standard body as an industrial expert in this field. He is a published author and regularly writes for the Fire Times. He has guest lectured internationally on PPE and medical textiles. With over 30 years of experience in European and Asian markets, Simon is an industry leader in this field. He's also a committed member of the TI Council and a fellow of the Textile Institute. So I'm very pleased to introduce Simon. Thank you very much, and over to you.
Thank you, Charles. Thank you indeed for that rather gracious introduction, and also like to thank Robert Hines for stealing most of my thunder. But however, Robert very kindly gave me his presentation prior, so my presentation will just be as a conduit to that particular presentation and cover some of the parts that maybe he hasn't done, but also to focus more on the role of legislation and standards. So if you would kindly move on to slide 2, please. So I want to sort of talk about the origins of fire retardant PPE, because it goes way back into history and using natural fibers. But the sort of real start of, if you like, PPE comes from the Industrial Revolution, industrial applications, but based around things such as smelting mills, where the use of woolen fabrics to protect the people from when they got splashed by molten metal, it would the fiber would then roll off. The fiber would then, if you like, burn, turn to ash, and roll the molten metal away from the actual garment and onto the floor. The use of leather has been extensive when dealing with thermal and heat applications. This has also led on to the fact is that with the industrial applications and the increase of industrialization, specialization, and military application, I've also then used leather and wools, and then later man-made fibers to increase the survivability of their personnel. And finally, it's like most of the key innovations have been driven from space exploration times, which was in the 1950s and 60s, with the birth of the aromatics, like meta-aramids and para-aramids, as well as PBI and PBO. And from this time, the extrusion of making fibers and then making yarns and then making fabrics spawned a whole new generation of PPE. The next slide, please. So, as already Robert's mentioned, application and uses, types of markets. I just basically wanted to cover some of the major markets that FR products are used in. So, medical wound scaffolding and dressing, and drapes and gowns, emergency services, personal protective clothing, i.e. high visibility thermal and or arc flash protection functionality, which Rob has very kindly gone through, with an increase in comfort requirements over the years. This is very, very true, because even in the highly technical products to do with emergency services, there's an increase in demand for comfort. Also the same with military, so thermal arc flash durability, invasive debris contamination. So it's looking at products that if there is a wound, that the actual textile that goes into the wound starts to self-sanitize, and lint or odor reduction, i.e. to stop people smelling, because obviously that's also another form of being found out. So also nautical applications, emergency response teams, looking at on the waves, obviously maritime nations and having big fleets, they all need servicing and they all need PPE with special applications within close confined quarters. And finally, as Rob and other speakers have mentioned, industrial, aviation, automotive, locomotive, oil and gas, energy production and transportation are all markets that, if you like, FR products are being used in currently. Next slide, please. So this is some of my background over the last 10 years. I've been highly and heavily involved with the fire market, especially with the development of new composite structures for the current fire service, and also involved with the current standards for wildland and for structural firefighting. Police as well, looking at products that protect the police while going about their duties. And then the final one at the bottom there is a product to do with bomb disposal. So these are obviously high energy, high impact, and it's just how to create a product that will keep the occupant safe from that particular risk. Next slide, please. So basically, I've just summarized it in certain areas. These are not everything. Obviously, there are some extremely fascinating new materials, biotech materials and stuff that are coming out. But in some of them, natural man-made fibers, animal and vegetable. So animal, you're talking wools. Vegetable, you're talking cottons. They have their own fire retardant properties. As Rob mentioned, they're extinguishable and they turn to carbon. They char and form a char surface. Modified cellulosics, synthetics, man-mades, and then finally metapararamids, or the aromatic compounds. Next slide, please. So the reason why still there is a room or a part for natural fibers is because they don't char, they are sorry, they do char, they turn to carbon, and they don't melt or stick to the skin, because predominantly a lot of the deep wounds that happen if a person is wearing products, as you saw in Rob's video, when you looked at the arc flash and then even the mannequin test, you could see that when a product melts, it sticks onto the skin, and therefore the burns are much more severe. So it's looking at where these materials and these fibers, where they sit within the overall scheme of things. And you can see some of them have very high ignition properties, but they need that, especially in these high-risk environments. Next slide, please. So on the sort of standard side, in the UK, Europe, and USA, the majority of flame and heat-resistant fibres and textiles are still chemically after-treated natural fibres, predominantly cottons. In the case of workwear, and the balance of about 20% is the inherent FR, which is your meta-aramids, para-aramids, or modified synthetic fibers. Next slide, please. So on the man-made fire retardant fibers, this just gives you a list of most of the predominant products within that field. So the ones that are mostly used are aramid fibers, the PBO, PBI. They're the ones that are the current dominant sort of fiber blends, or fibers that they can blend with other products for these systems to deal with things such as a structural firefighting gear or wildland firefighting gear. Next slide, please. So that just covers a bit of the background of the history, where it comes from, where things are, where we've got to. I just now want to talk about legislation for PPE. It's obviously the health and safety regulation and what that means. For the standards bodies, what it means is that they have to, when you are part of a standards body, you, especially in the UK, you have to look at the order of precedence. So the ISO, international standards. So we should all be looking at international standards as the way forward globally, but then regionally, the SEN standards, especially now that BSI have still signed up to the for the foreseeable future to follow the SEN standards, EN standards. That is still relevant to people within the UK. And then where there is deemed necessary, like for instance, there is a standard, that BS standard that was released just recently for the fire service to do with cleaning and maintenance, because there wasn't deemed to be a standard that could give some advice to the local fire service or the national fire services in order for them to help and make the right decisions on cleaning. So what these comprise of are bodies that brings together experts that share knowledge and develop voluntary consensus-based market-relevant international standards that can be then used by the marketplace to supply the end user. Next slide, please. So I've taken these from the ISO. So what are standards? So basically they're published documents setting out specifications and procedures designed to ensure products, services and systems are safe, reliable and consistently perform the way that they were intended to. They establish a common language which defines quality and safety criteria. These are the minimum standards required. So if all else fails, they've got to achieve this particular standard. So these documents are meant to be practical and not set impossible goals, which is why the minimum standards are required. They are based on sound industrial, scientific and consumer experience and are reviewed to ensure they keep pace with new technologies. And they require key representatives to participate. Next slide, please. So I've put this slide on here because it's got the chicken and egg. So what comes first, the chicken or the egg, the famous story? So the way that I like to put it is that either way, what comes first is that if there's a need and there's a reason to create a standard, then that's driven by the end user, the person that's going to use it. So within a group of people, there's always the end user, the test house, and the manufacturer. So the manufacturer makes a product for the end user, and the test house is a certifying body that says that this product fits that and conforms to that standard, therefore can be used by the end user. Now, the Americans have a very good way. They have a 1/3 rule. So in each standards body, they have an end user, a manufacturer, and a test house. So they have equal representation of all. That isn't necessarily true in most of the European standards, but obviously a lot of this is driven by the end user, because the end user has a practical knowledge of what they need for their given market space. Next slide, please. So how are they used? Manufacturer uses them, obviously, to make the PPE to a consistent requirement to industrial specification. The test houses use them for independent certification to validate compliance, and the use of the standard leads to an end product that in the end user can be assured is fit for purpose. So the end user specifies by doing a risk analysis and understanding what particular standard gives them the best form of reaching this risk analysis, which then the manufacturer has to follow, and the independent test house or certification body then certifies to that standard. Next slide, please. So recent improvements and the innovation. I know that Rob's covered some of this as well, and even on some of the other presentations, especially the grass one and others, smart technologies are coming more and more into the field now. Active smartware such as illumination and sensor technology. I've seen some technology which is using telemetry, especially inside buildings, for either the military or for the fire service, because generally what they do now, if they're committing firefighters into a building, they're still using old-fashioned rope to go in, and they're still using an old-fashioned board which they write times of people going in, times people coming out, especially when they're committed using BA gear. So this technology is coming into the limelight. It's becoming cheaper, it's becoming more accurate, and it's becoming much more viable to use it in these areas. Human psychological performance trackers. This is also about stress. There's been some big studies done on heat stress to do with specific tasks within the firefighting industry, because sometimes heat stress can cause bad decision making, and can lead to risk and danger to life. Which is where comfort and heat management systems are also coming into play. These are passive and active. So passive technologies are things like using different fibers that give wicking and absorbing functions. As Rick also mentioned, is that sometimes if a product is too wet, it then lets the heating, as it's thermally conductive when something is wet, it lets through the heat more and therefore causes more heat stress. So it's how to manage the heat stress, and also to be able for that firefighter to continue their duties whilst in that dangerous environment. Next slide, please. So on the standards, there's a bit of, this is where the chicken and egg story comes in. Sometimes new innovations that come into the market space come in, and they're that new that the standard that would apply to has not gone through their cycle. So for every standard is looked at in a 5-year cycle, generally speaking. It's done a peer review. And within that, the questions are asked, is the standard fit for purpose? Are there elements within the standard relevant and appropriate or redundant? Like, for instance, within the standard, there may be several different test methods. And are there different test methods that would be more accurate or more up to date? Or are there test methods that need to be made redundant because they're no longer relevant, because they're not accurate? And this is where also you'd be looking at things like different forms of standards. Would have, like for the electrical side, it's the marriage of the electrical side with the textile side now, where they're now looking at hybrid standards in order to accommodate some of these new innovations, especially on smart garment technology. But all this, of course, is end user driven. And it's also, do we have a way of measuring new innovation within the standard? So this is all captured within the 5-year peer review. So technologies that are coming in obviously now have to be reviewed and looked at, especially things like smart garments and active technologies, as well as passive. Next slide, please. So that's the end of my presentation. Thank you very much indeed for giving me the opportunity to dovetail into Robert's presentation, and I look forward to any questions and answers later. Thank you.
Okay, thank you so much to Simon, who's a course tutor on the TI's excellent short course Textiles, which I'm sure most of you are familiar with. If you aren't, please visit the Textile Institute website, and we can highly recommend those. So now we're on to the Q&A session. So I'm going to ask the panelists, if you can please, to switch your cameras on. And there's one additional person I would like to introduce to you this afternoon, and that's Rebecca Bennett, Becky, who's our secretary, and has been working tirelessly to help to get this event up and running, along with the TI staff as well. So yeah, where shall we start?
So shall I pose a question to you then? So we've had some good questions come in on the QA stream and on the chat stream. Lots of love for artificial grass, it has to be said. But first question goes to you, Charles. So we've had the question from Subian, I think, apologies. Is there a potential to use spacer fabrics as face mask protection? So the assumption that their filtering characteristics would be good for preventing the entry of the virus into the respiratory system.
Okay, Raj, thank you very much. Good question, and something which is close to my heart. Yeah, the answer is yes. I have to declare an interest that Boltex developed a face mask using 3D spacer fabric when the pandemic started. obviously because of the structure of the 3D fabric effectively is a knitted fabric, double face knitted. So there is a limit to the filtration abilities of the 3D spacer fabric by itself. So we did some filtration tests and we found that the particle size that we could capture was relatively large. We overcame that by using an antiviral finish, silver-based, which kills the virus on contact. But of course, you appreciate that a lot of the most of COVID are actually nanoparticles. There are many other companies who've developed face masks using spacer fabric. One of the probably most prominent ones is Under Armour from the States. There's quite a few others as well, and they've tended to use non-woven materials, filter. The benefits of a 3D spacer fabric is that they're elastomeric materials, so they're very conformable. So you get a very good tight fit around the face. But the best ones, companies that say like Under Armour, have developed the high quality, high performance masks, and there's quite a few of those.
Thank you very much. Comprehensive answer. Next question goes to our two firemen. So Simon and Rob, you can fight over this one. So obviously you've talked a lot about the raw material that the flame retardant fabric is made from. The question is, does the textile construction, i.e. whether it's a weave or a knit, have a significant influence on the flame retardant property, or is it mainly the material or mass of fibres present? So either Simon or Rob, over to you.
I'd like to go first if that's possible. Sorry, Rob, if I'm stealing your thunder. No, it's only a part of it. I mean, I did. There is a lot to do with structure as well, because it's about how you create a void as well, and the so knits as well as wovens also, and the construction of either does complement the sort of thermal efficiency of the fibres. So the fibres are only part of it. It's then also the structure and how it creates space or void within that, because most of the fireman type products are composites. They're 3 to 4 layers, and so each layer has a different and specific role, but as an overall function, they all work in harmony together to combat some of these extreme temperatures that the firemen have to work in.
Yeah, and I would really just completely agree with Simon on that. Like I've seen quite a bit as we think about like the arc flash hazard. A great example is like a jersey knit compared to an interlock, where you've got like with an interlock fabric, you've got kind of almost 2 fabrics knit together, and you've got that airspace, just like Simon was mentioning. It's a huge insulator. So you might get a couple more calories of protection with fabric structure using an interlock compared to a jersey. And I think the other thing, materials like fibers and raw materials, very important. Different fibers absorb different amounts of thermal energies. Like carbon's is super absorptive, so it's super helpful, but it's also kind of weak. So it's kind of that right blend of fibers. And one of the big things, I guess, again, with like just the arc flash piece and the flash fire piece, is you just want to try to avoid a situation where the fabric will break open. Like if an arc flash hits the fabric and that fabric just pops open, then all that thermal energy can transfer through to maybe the undershirt. It might light on fire, like a cotton t-shirt, or hit the skin, something like that. So yeah, it's absolutely important how the fabric structure is there, and also important with the raw materials that they're sturdy enough to resist that initial impact of whatever kind of hazard you're going to be hit with.
The only thing that I would add to that is that there is a lot of looking at selection of fibers and placing fibers within the fabric structure. So a lot of the fabrics that are used within this particular environment are double faced. So they'll have a two functionality, and that's both knitted and also woven.
Cool, thank you. I think the videos certainly spoke 1,000 words. I like the arc flash. What does the second do? A lot. we've had loads of other really good comments and questions, and I'm conscious of time. So I'm just going to pose one more, which is on a bit of a hot topic. And I'm going to fire this one at you first, Stephen, but I think it's obviously going to be hugely relevant to everyone. And this is a great question that's come in from James, looking at the fact that they've at kind of Martin Baker Aircraft, they utilize a wide variety of technical textiles, but at relatively low volume. Some fabrics are coated, others specialized. And they're looking for ways in which they can recycle or donate the fabrics and scrap materials when, you know, if they're not needed. And therefore because they've got low volumes, they're not big enough to interest recyclers. And has anyone on the panel got any thoughts on where they can turn? As I say, I'll pose that one to you first of all, Stephen, because I've been kind of privy to many conversations with you about recycling, and I'm sure that you can give a good overarching kind of answer to this. But as I say, anyone else on the panel, please feel free to jump in.
Yeah, okay. I hope you can hear me all right.
Yep.
Yeah, good. No, okay. So the problem there is not so much about the value of the recyclate, but the volume, I think, right? Because it's quite surprising what does have commercial value at the end of life, because fundamentally that type of material has functional properties still, even though it's no longer suitable for the first purpose. So the sorts of things that people are doing there, and this assumes that it's not possible to, by the way, before I start, this assumes that it's not possible to design for the end of life at the beginning, which is the best way to approach it, you know, and also not to make stuff that doesn't go into the final product, you know, so you don't make waste in the first place. So assuming you can't recycle it as post-industrial waste, so it goes back in as a blend component to make what would be effectively a virgin product again. In the recycling industry, of course, it's also very common to blend. So to think about how, you know, X% of that waste could transform the performance of a blend for another particular application. So a similar process to what might go on if you were designing a first use product means that you don't need such high volumes to make it work. It also means that we increasingly need to look at niche applications for that waste rather than high volume applications for that waste to make it worthwhile recycling. So without knowing more about the materials, I think it's difficult to say, but I think the starting point's mechanical recycling. Other methods of recycling, like chemical recycling, of course, are developing rapidly, but they have environmental impacts too. So nothing that we manufacture, very little that we manufacture, has zero impact. But increasingly, what I'm seeing is you know, and this is driven by cost, is not making or trying to design out waste in the first place, recouping or recovering post-industrial waste for making the original product. And if that's not possible, also pooling that type of waste with other sources, which is weird because it means cooperating with competitors potentially to find an economic way of giving it a second life through recycling. So I think, you know, those are my initial thoughts based on the way the question is posed.
Cool thing. Would it be fair to say that obviously recycling is a hot topic both for kind of clothing textiles and for technical textiles? Is it fair to say that it's a difficult task to find places to recycle technical textiles as it is to find places to recycle kind of textiles that are currently used in clothing?
There's plenty of technical textile material that is recycled because the physical performance of those fabrics are valuable. Okay, so, you know, one very simple way to devalue it is to have other material in there that, you know, when the whole thing is shredded down, means that you're not actually quite sure what the composition is because it's been diluted. But you can do a lot there by just thinking a bit more carefully about the design of the original product. So what comes through for recycling is either homogeneous, it's made of one material, or it's a known composition, fiber A, fiber B, chemical coating, X, Y, Z. But there are recycling companies today who are taking technical textile waste and converting it into other products that have a very long, potentially, service life. So I know we talk about downcycling, but effectively that's what we're doing with recycled polyester in clothing, isn't it? We're downcycling plastic bottles designed to take carbonated water. But the point is, closing the loop means also ensuring that there's a second economically viable life for that waste. And I think the recycling industry, which is very well established in the UK, of course, we effectively invented the shoddy process back in 1813, or whenever it was. It's quite surprising what can be recycled if we can get our hands on it. And you only have to go back through history to see just how much waste has been recycled in the past and the unusual products into which it's placed. So there are plenty of consumer products on the market today. Even back in the technical textile industry and the automotive industry, a lot of textile waste is used routinely. It's just that we don't see it. It's hidden.
Yeah. Thank you very much. Is there anyone else on the panel who wants to add to that? Or Charles, I think we're pretty much good to wrap up.
Probably, I think I might just I think one of the interesting things about the topic that we're talking about here is that it is, as you say, it's all about material and whether the material is homogeneous or not. And I think that going back to the textile definition of technical textiles, that it may be helpful to actually think about materials in terms of fabrics, in terms of actual raw materials itself. Jonathan Jewell raised the point about, Stephen, you just mentioned that if you design your product at the outset with the thought to end of life, if you've got, for example, from James Lorbiecki, a material which may have aramid in it, for example, there will be associated industries, whether it's hot gas filtration, for example, where that material could go, or even, for example, recycled Kevlar going into motorcycle jeans. But it's identifying what those pathways are. And I think that's a really interesting topic and conversation. And one of the things we're hoping to do within the Technical Textile SIG is to join different parts of the industry together, people who normally wouldn't have those discussions and wouldn't think in that way. So it's great to hear that there's probably more recycling going on than we actually realize. Thank you. So aside from that, we will be looking to hold quarterly events with the Technical Textile SIG. Obviously, it's a new organization. We've just been set up. I'm very grateful to all of our panelists, all of our speakers today, for all of you who've joined us as well, and also to the Textile Institute, to Stephanie, the CEO, and also to Robin and Ellen, who've worked really, really hard. As I say, and many thanks once again to Becky to make today happen. So really, thank you so much for joining. This presentation will be uploaded to YouTube, so you can share it with, and I encourage you, please, we'd like to encourage you to share it with your colleagues and contacts to push the word out, and we will be in touch and look forward to engaging with you again. Thank you.